Hey everyone. Thank you, Catherine, for the introduction. So my name is Michael. I'm a data scientist here at AppNexus, and I research invalid traffic or all sorts of other, bad things that happen on the internet, and I get to use computers to try to find it. So I'm going to talk to you a little bit today about some of the ways that we're looking at the problem, some of the findings we've had. I've got a bit of some results to show you. I'm going to go through how it all kind of works and describe the technology a little bit, and hopefully you'll all find it interesting. So. Let me just advance. Okay, so yeah, agenda is to talk a little bit about what is streaming in terms of how we process data. What is Spark specifically, which is a tool we use to deal with all this stuff. What is this invalid traffic we're looking for? I'm going to go through 3 examples of how we're using these things to find bad stuff, and there's going to be time for questions at the end and also interspersed in the middle. So without further ado, okay, let's talk a little bit about what is streaming. So streaming is this way of basically moving data around between computers, and it's really helpful in situations where you have a lot of it. And the main idea of streaming data is that in contrast to other technologies that have been around for a long time is you just don't store the data on a hard disk. You just say, I've got a computer over here, it's making things, and I send it to another computer over there, and I do stuff with it, and it never gets stored to disk, really. So this idea of ephemeral data movement is sort of what it is. It actually has a lot of advantages. One of the big ones is that if you operate in this manner, you can make some useful assumptions about how things work. Like, as an example, if I have a bunch of numbers and I got to find the top 50 numbers every 15 minutes or something, I'm willing to tolerate a little bit of uncertainty on the ordering of the numbers potentially. You can have a really big benefit for this, and you can save a lot of time and money. So there's this package that we use, or 2 of them actually. One of them is called Spark, another one is called Kafka. And I'm going to talk to you a little bit about how we use them to find this bad stuff, or really any problem generally. And it helps us because some of the data we're looking at is somewhere between 40 and 60 megabytes per second, or about 3 terabytes a day for the particular records that I'll be discussing. And it's just would be a lot to deal with on a small number of computers or whatever. And we also are interested in doing it quickly. So like other kinds of fraud that happen on electronic systems like credit card fraud or hacking or anything like that, you want to be able to react really quickly to bad stuff that happens. So being able to do it in a streaming manner saves you the trouble of having to wait till the end of the day or something, or wait until the end of the hour to compute some sort of an answer to the problem you're working on. So it has a lot of advantages. But we should also talk about why should you not use it? Because there are situations where it's inappropriate to use streaming technology. So one of the things that's really a big part of all of this is that modern computers have memory, which is quick storage. It's a lot faster than a hard disk, and it's cheap. So if your data can fit in all of it, it makes a lot of sense to just keep it there. But if it doesn't, then you need to come up with a different solution. So in that case, a streaming answer is really not the best choice. One of the examples where this is an important thing is when you have to do, you say you have 2 logs, and you want to find records in one log that are the same in another. So that operation is called a join. And if you need to, say, look back to yesterday to do a join, it's a bit of a problem. So it's much better to keep that in a shorter window, like 10 minutes or something like that. So streaming technology really doesn't work well for that kind of stuff. Another problem with it is because it's sort of ephemeral, which is the main benefit, if something goes wrong and one of your computers has crashed and you have to restart the whole process, it's not exactly so straightforward to get your answers back. But the problem with this, there's ways around that, but then you sort of lose the advantage of this ephemeral data that doesn't really exist and just goes away. So you can save it, but it's a problem. So finally, the other thing is that it can be a little bit more complicated because a lot of the technology that runs all these systems is sort of new. It's not quite as mature as the stuff that's been around for a long time. And there's also another dimension involved in all of this, which is time. So if I just want to say, I got all this stuff over here and I want to add it all up, that's pretty easy. But if I say I want to add it all up every 10 minutes, it's quite a bit more complex of a problem. So, all right. So with that, I want to change gears a little bit and describe sort of in some detail what happens when we serve an ad on our platform. And as Catherine was saying, there are quite a bit of them. So what happens basically is on the left here we got 2 boxes, or actually many boxes, that represent what might happen on a user's computer when they're on some website, such as the New York Times or something. So their computer has an IP address, which is sort of like a street address for your house. It's a unique identifier that says where you are on the internet. There is a string called the user agent, which is submitted by your browser that tells the server on the other end of the connection what kind of browser you're using. Is it Chrome? Is it Firefox? Is it Internet Explorer? Are you on Windows? Are you on a Mac? Is it a phone? Yada, yada, yada. We know the web page that you're requesting an ad from, so are you looking at the New York Times and you want to see an ad or whatever? And what happens is this request heads over the internet towards our server, and it runs into an application called the impression bus. And at that point, the impression bus is going to do all sorts of stuff that is the platform thing that we're talking about. And it'll take care of an auction that will say, who wants to pay the most right now to show this specific impression? Who wants to buy this impression? And then what happens is that auction is concluded or it's not transacted or something, but in any case, we have a record of this auction taking place. And this happens as much as, probably, I think, 150,000 times a second is what I'm looking at. And all this information comes out in logs that we have. And it goes out through these applications, additional applications we have. One is called PackRat, and then PackRat takes these logs and then moves them into a system called Kafka, where I can look at it using Spark Streaming. And I'll talk about what all that means in a minute. But that's basically how it all sort of fits together, is that there's this large flow of data that just is all over the place all the time. It's like a fire hose. And we have a lot of it. So, all right, so I mentioned that we're using this thing called Spark. And what is Spark? So it's a system that has come out of the University of California, Berkeley, in the last couple of years. It's very promising, it's very exciting, and it really takes advantage of the fact that computer memory is very cheap these days. And what it does is it lets you just say, I've got a bunch of data, I want to load it all into the memory on, say, 200 computers all at once, and I want to just do things to it, like I want to add it up, I want to count things, I want to find the unique things, I want to sort them, whatever you want to do, it lets you do it. And it has this thing called a resilient distributed data set, which is sort of this thing where you can say, I've got a little program here, and it's got all this data, and I can just do things to it with this RDD. And it also has this sort of a second layer of it, which is if you have an RDD that changes every certain period of time, that's called the D stream. So I'll show you some examples of like how this works, but we can say every 10 seconds I want a new RDD or something like that, or every minute, or every 10 minutes, or 5 minutes, or whatever you want. And I can say I want to count the top items every 10 minutes or something like that. So it's very powerful and very fast. I should mention, though, that Spark's not the only thing out there. There's other packages that do the same thing. There's at least two other ones. One is called SAMZA, and we're using that at AppNexus, although I don't really know anything about it. And there's another one called Storm, which is from Twitter, and that one is also very promising as well. So the other thing, though, that is involved in all of this is this thing called Kafka. Now, what is Kafka? It's a similar idea to Spark. It's a package. It's originally from LinkedIn that lets you deal with large amounts of data in a pretty easy way. And it facilitates this whole streaming thing I'm talking about. So what you have are these things called producers, and they produce messages for a particular topic. Now, our producer is PackRat, and then our topic is transacted auctions. And then there's a bunch of brokers which organize all of these messages in the topic to different partitions. And then each of the consumers can connect to individual partitions and download messages, and it's supposed to keep track of everything, so it's just very easy. You just say, hey, give me the messages, and then they appear, and you can do things to them. So it's pretty cool. So, and fortunately for me, as a data scientist, I don't have to worry about most of this stuff. It's all abstracted away for me. And we have a team of people known as a Data Engineering Real-Time Platform, or DERP team, that helps us with all these things, and they are fantastic for allowing me to just do whatever I want and not have to worry about it too much. So it's very cool. Okay, so let me just describe how some of these jobs are set up. Now, we use a thing called Yarn, and Yarn is another system that's part of a Hadoop, which I'm sure many of you have heard of. It just allows you to schedule resources on a cluster of computers. And we have large amounts of computers that we use for processing all the data we have. I think the cluster where the jobs I'll show you running right now are as many as 500 individual servers, all with 16 cores, and so they're quite a bit of computing power. So what happens is we run our Spark job on a Hadoop cluster that's running Yarn, and the Spark application is just sitting there. It does its thing. It churns every certain set period of time, and we consume records from Kafka, and we do things to them, and we send them out to either Postgres for storing the answers for further analysis, or to use or to take action on them by making changes to an API. So basically, everything on the left side of this figure, I don't really have to worry about. It's all there. It's really fantastic. So I'm everything from the Spark application over. So as working as data scientists, we're really very happy about this, stuff. Okay, so shifting gears again. Now that we've talked about all the computer stuff, let's talk about what's going on here with invalid traffic. Now, what is invalid traffic exactly? It's a little bit of a kind of a fuzzy thing that most people don't really know is going on even, but it turns out that a lot of the ad impressions that are on the internet aren't generated by humans. They're generated by robots of some sort. And that's obviously a problem because, if you're an advertiser and you're buying ads and 30 or 40% of those ads are just being shown to robots, well, it's kind of a bummer because you've got all this money you're spending and you want it to be doing something useful. So that's something that you want to avoid. And you might think like, well, okay, well, I'm just a person who uses a computer. Why do I care about this stuff going on? And the answer is because it leads to a lot of additional problems on the internet. So a lot of people who want to make money doing this, invalid traffic and generating fake impressions, they do it using computer viruses. And what they'll do then is they'll go and they'll just write viruses and they'll find ways to get them onto your computer. And there's malvertising, which is when people put viruses in ads and try to send them on the internet. There's all sorts of bad things that happen when you have this ecosystem of malicious activity. And it probably even is helping fund organized crime. Now, not organized crime like, Goodfellas, like that, but it is, probably some people in Eastern Europe or Southeast Asia or something who are just doing this to make a lot of money, and it's real bad. So the way it kind of works is pretty interesting. There's a lot of really interesting financial incentives and sort of a parallel economy that goes on. And what happens is you have these publishers, and they may intentionally or unintentionally be part of this scheme where they basically pay what's called a traffic exchange. They pay them for visitors. So there's places you can go on the internet and you can say, I will pay you $1 or something, and every time I pay you $1, you send a visitor to my site, or maybe it's 50 cents or $2 or whatever. And these traffic exchanges some of them are fine. If you think about it, in certain ways, advertising is all about traffic exchange. I mean, Google AdWords is to get people to come to your site, so it's not all illegitimate. But certain of these traffic exchanges are not very scrupulous about where their visitors come from. Now, there's some sort of a question mark situation here, and money launderers and we don't know what. But at some point, money goes from a traffic exchange to people who write computer viruses or operate data centers or something, and the bot herders in this case, and then they have these computers they control, whether they're by viruses or computers they just rent from Amazon Web Services or something, and they have their infected users go visit the publisher's website by making a redirect through the traffic exchange. So from the publisher's perspective, they pay money to the traffic exchange, and the visitors just show up, and they just look the other way because we don't know if these visitors are bad or good, and they just arrived here. And then they're able to sell the ad impressions that are generated. So that's sort of how the money flows. Now, another crazy thing about this is it turns out there's even affiliates within the bot herders. So if you want, you can go on the internet and purchase 50,000 infected computers to do whatever you want with. And there's this other crazy economy of bot trading that goes on. So it's really very fascinating. And I think if you're an economist or a business person, there's a lot that would be really interesting to learn about. But that's unfortunately all we can talk about. Another interesting thing here is that there's a lot of game theory that's involved with all of this. And this is in the sense of how security works for antivirus companies, for AppNexus. I can't tell you all the things we're doing, even though some of it's very interesting, because it's conceivable that some of you in the audience may be people who run these things. And so if I tell you everything, I mean, you're all probably very savvy people. So if I tell you all the details, and you might use this to take advantage of us. So I unfortunately can't give away all the exciting scientific details or technical details or anything like that. But suffice it to say, even if you walk away sort of unfulfilled at the end of this, it really goes in a lot of different directions between economics and business and computer security and research and math and science. So it's a fascinating topic. And I'm told that if you feel unfulfilled, it means it was interesting. Okay, so I'm going to talk about 3 specific examples now that we've gone through all the background. And what I'm going to talk about are we do something called streaming sessionization, where we look for sessions of users that are irregular. and I've got some demos for that. We'll talk about user agents, which are this sort of like the model number on your browser, if you will, and we'll talk about co-visitation. So let's talk about one of these examples here. So the session analysis thing. Now, I was mentioning earlier that IPs are useful for us, and the reason for this is because they're somewhat permanent and they're a somewhat universal identifier everywhere on the internet. So if I have an IP address that I know is a malicious IP or they're sending a lot of bad traffic to us or whatever, we can just send a rule to our firewall that says, hey, any traffic coming from this IP address, we don't want to serve them any ads. So it's an effective way for us to quickly stop the flow of money to certain of these bad actors. And if we can do it in a fast enough way, and this is why streaming is handy, if we can do it quickly enough, we can just change the incentives of generating this invalid traffic, and we can make it harder and more expensive. So it's an arms race. And what we're doing here is we're defining these sessions as all of the activity from a certain IP address in a period of time, and we want to look for sessions that are egregiously non-human looking. So if you're a single computer that generated 1 million ad requests in 10 minutes, as an example, we're pretty confident that you're not a human, and we're not going to take the risk that you might actually be a human, and we're just going to shut you down, even if we can't really ever know for sure. So one of our filters that does this identified approximately 12,000 bad IPs last week, or about 1,600 a day. And so some of the things we find from this are pretty interesting. One of them that I had an experience with recently was it was a computer at the University of, actually I probably can't say where it's from, but some university had a computer that got hacked, and they were sending us something like 500,000 impressions every 10 minutes or something like that. And so we called them and we said, hey, there's something's the matter, what's going on here? They said, oh, we actually got 5 other phone calls already this week. Someone broke into one of our systems. So we're looking for things like this. Another thing is data centers they're everywhere now. So there's companies all over the place that for a small fee will just let you rent a server from them. And they pop up and go away, they change, and they're very flexible, and anyone can have one. So I think a couple weeks ago we found one that I thought was a very funny name called Joe's Data Center LLC, based out of Kansas. They're blacklisted now. So and it's also useful for looking for big variations that happen within a day. So analogous to how credit cards work, if you purchase, $10,000 worth of appliances in 5 minutes, usually we'll probably get a phone call from your credit card company. We're looking for that sort of stuff. And if you see a big change, it's very informative. So we implemented this in Spark Streaming. The example that I used to generate the data I just told you about operates on 600-second batches, which is pretty handy. For our purposes, we find it to be more or less useful. Although, rest assured, we're not just doing this. So if you get any ideas, we're looking other places as well. Basically, we will run the batch every 10 minutes, and then we will aggregate and blacklist IPs that are malicious. The nice thing about it is there is pretty linear scaling for all this stuff. So if we need to increase or decrease our capacity, it's very easy with Spark just to say, hey, give me another 10 computers, give me another 5 computers, whatever. So it's cool. Or take them away. So this is actually a program that I am running right now, as a matter of fact. And it's written in Scala, which is a programming language that you can use to work with Spark. And basically, this is pretty much it. So this code, minus some stuff I took out for readability, is going to run on, I think, about 50 computers all in parallel. And it's 15 lines. So basically, the first little bit of it is just to identify what this application is called. And then I've got some utility functions that I didn't show you. But then I'm just going to set up these little objects here called a Spark context and a streaming context that allow me to manipulate the data or talk to all the computers all at once, basically. And then I connect to Kafka. That's the next 4 lines. And then I join things together. Then I just will add up and count the number of IP addresses and look at the number of impressions and look at the number of domains. And that's it. So this is really one of the things we really like about this is that it's just so simple. And as a data scientist, I can sit here and write this code and very quickly and just run it. So it's great. All right. So I also have an example of an IP address that we identified recently. So this one, this IP address was found in our system recently for having violated some of these thresholds I'm telling you about. And you can look it up on a system using a tool called Whois. and you can find out who owns a particular IP address, because it turns out that IP ownership information, much like street addresses, is public knowledge available to anyone on the internet. So this particular IP address belongs to some company called Global Frag Networks. And it turns out they're a hosting company. So you can go on Global Frag's website and you can just go get a server for a certain amount of money per month. And this is an example of someone who we don't want to serve any ads to, because it's very likely that we think that whoever's on the other end of this IP address is not a human. And so I actually went and looked at the websites they're looking at. So this is from that same IP address, and it's for just today. And I can assure you that all of this it's been blacklisted for some time now. But they generated, in the span of one day, approximately 12,000 impressions on 2 different computer news websites, or 24,000 in total, and a bunch of other ones on games websites. So there's actually quite a few more that on this list, but it's an enormous volume of traffic that is coming out of this one data center. And thankfully, we were able to find it and turn it off. All right. Now, before I go on to the next section, which is talking about user agents, I want to stop to see if anyone's got any questions.
There are a finite number of IP addresses, and you could be blocking up to 1,600 a day. What's your criteria behind unblocking these eventually?
That's a great question. We have criteria. We thought about it. Oh, the question was, how do you unblock IP addresses because there's a finite number of them? And the answer is, we do it. Okay, so let's talk a little bit, move on to the next section. We'll do more questions later. Let's talk about user agents a little bit. So as I was mentioning, user agents are really interesting because it's basically a chance for someone to say who they are. And there are certain things you can do that are really interesting with this information. So as I was saying earlier, if you're running Google Chrome or Firefox or Internet Explorer or whatever, your browser will say, hey, I'm Firefox, or hey, I'm Google Chrome. So we can do things like browser introspection. So if you're claiming to be Internet Explorer, but you don't have JavaScript that acts like Internet Explorer, that's really suspicious, and we're going to treat you very carefully with, assuming you're probably a malicious user trying to make money. Another thing, though, with user agents is they're unstructured text. They're huge, long strings. They're 512 characters. So if we were to store them somewhere in a database, it would be very difficult to work with them. They're about 500 bytes, and that would come out to be around, for just the user agents on the platform and nothing else, about 4 to 8 terabytes a day, depending on the amount of data. So one of the things we can do with them, though, is that they're hashable, so we can just convert them to a hashed representation and store the hash table. And doing this in streaming is really nice, and that's actually what we do. So I have a demo of the user agents on the platform, and here they are. So this job has been running for a little while now. I hope everyone can see it okay. This is running right now on production data. And you can see that in the last, this interval is set to 1 minute. So in the last minute, we had approximately 145,000-ish impressions from Mozilla 5.0 running Apple WebKit, which is actually Google Chrome. So an interesting fact that was actually pointed out to me earlier today, I sort of forgot about this as an aside. It turns out that every browser on the internet these days claims to be Mozilla. Oh, it's running a patch. And the reason for that is it actually comes from a long time ago when Netscape was the dominant browser on the internet, and other browsers that wanted to, just use the World Wide Web would claim to be Mozilla so they don't confuse servers. Now it's sort of like a rite of passage that every browser claims to be Mozilla, even though Mozilla, as it was back then, hasn't existed for some time. So it's a pretty interesting little artifact. So regardless, though, you can see that there's a variety of different user agents here, and it's very unstructured, hard to interpret text. So you have you see the first one is Google Chrome, which is probably not terribly surprising because Chrome is a very popular browser. But down below you have, this is Internet Explorer 7, and then there's Firefox is in here. You can see some iPhones, you can see Macs. So there's a variety of different user agent information in here. It's very, very detailed, and there's quite a bit of it. So now, let's go back to that IP address I mentioned earlier. Now, this is that 104 IP address. That is the Global Frag network. And these are the top 5 user agents that we saw from that IP address today. And remember, this is one IP address, and they're claiming to have all these different kinds of computers. So they're running Chrome on a couple different versions of Windows. Apparently, a couple different versions of Internet Explorer. It's not shown here, but they also have iPhones and iPads and stuff like that. So if you're into statistics, you could do things like, given the prior distribution of browsers on the internet, what are the odds that you would observe exactly 125 impressions or 130 impressions or whatever from all of these browsers all coming from the same IP address? So there's a lot of really interesting math and data science research you can do based on this information. And unfortunately, I won't go into details on it, but it's cool. So here's another example of some bad user agents that I collected a little while ago. Now these ones are examples of programs that are probably not ones you want to serve ads to. So the first one up there is wget, is a utility that you use to download web pages from the internet, and it only runs on the console like I just showed you. So you can't even render images, so you probably don't want to serve any ads there. There's also someone who got a new iPhone, apparently. There's another Apple iPhone. There's a Python URL lib in there for those who know Python. A couple undefined, Spice, untrusted, whatever that is. And we see another one called curl, which is another utility for downloading web pages. So there's a lot of really interesting stuff in here. And these are examples of user agents that are probably suspicious. On the other hand, again, these are ones that, like the ones I just showed you, are more normal-looking user agents, which, of course, can also be forged, but it's really a little bit more difficult to figure out some of this stuff. There's really bad examples of this stuff, and there's more subtle examples like the one I just showed you from the global Frag network. So it's cool. All right, let's move on to the next topic, which is session similarity. So this is a cool thing where basically we can look for IP addresses that behave pretty similar for mysterious reasons. So as an example, let's say we have two users, A and B. Little typo on that slide. Okay, so user A visited Google and then Facebook and then MSN. And remember, we know this information because we know the IP address of the person who requests an ad, and we know what page they're on when they're requesting the ad. And then user B visited Google, ESPN, and New York Times. And we can use a measurement called the Jacquard distance or Jacquard similarity to figure out whether or not someone is, or how similar two things are to each other, given that we have these sets. So in this case, the similarity here is 20%. So they both visited Google, and there were 5 domains in total between both the users. So this is something we use quite a bit to determine whether or not there is suspicious similarity. The idea is if you run a bunch of computers that you control, whether they're bots or servers you rented or whatever, you want to make a lot of money, so you're going to try to send them to a bunch of websites that you're getting paid for them to go visit. So if we see IP addresses that have suspiciously similar co-visitation, as in they all go visit the same 5, 10, 15, whatever web pages, it helps us identify where we need to do further research or what we should shut off. So this has been something we've been working on for a while, and it's been really powerful for us. And it's cool because if you are making money with illegitimate traffic on the internet, we can find you because you want to make as much money as possible. So the thing we use to find you is your same incentive. So it works nicely for us. We're using a min-hash algorithm on the set of visited domains to get the answer to this question, and we're doing it in streaming. We also are able to do it offline as well using batch processing, but it is cool in streaming. And the problem, though, is that it runs in O(n)² time complexity, which is a little bit frustrating when you're working with batches, but it's quite a bit more manageable in streaming. So I'm actually going to show you a demo of this running live. And the output you're going to see is an IP address, another IP address, and the percentage of their similarity. So, all right, let's go to the console. All right, so here we are. Now this has been running for some time. This is running on our Hadoop cluster in the LAX data center. And let me zoom in a little bit. Now, so you can see, if you look at this last batch up here, you can see that the top 2 IP addresses on the platform, 104.148.13.58, 104.148.13.53, interesting, they have 95% similarity. Now, remember that other IP address that I told you a moment ago about the global Frag network? Guess who owns those top 2 IP addresses that are 95% similar? Which, by the way, happen to be right next to each other in the same allocated block. It's all the same people. It's a global Frag network. So whoever's running fraud on these invalid traffic on these. Oh, it's running a batch. Whoever's generating these invalid impressions is doing it on a bunch of servers they rented from these same people apparently. So it's a very powerful tool for us to identify this stuff. Now you can see that fortunately there's not a huge number of those IP addresses because this list is sorted in descending order, and you can see that by the time we get to the bottom of the list, it's down around 60%. So there's fortunately, or unfortunately, I suppose, depending on how you look at it, not people who are egregiously bad at this kind of stuff. But anyways, so that's pretty much it, I think. Oh, I have a conclusion. All right. Yeah, so finding invalid traffic is an intersection of quite a few areas. There's economics, there's business, there's computer security, there's data science, there's some cool programming, and there's math. And Spark is really helpful for all this stuff. Spark, Kafka, streaming, all of it, it's very exciting. And there's a lot more, of course, that I can't tell you about for obvious reasons. But if you want to learn more, you could work here, and then you get to know all of it. So, all right, and then I think we'll take some more questions now.
Hey, what are the business considerations that influence the decision between precision and recall in finding these IPs?
Yeah, I guess I'd say as sort of from a business perspective, the concern is, one of the big ones is, as I was mentioning earlier, like making sure we get false positives and false negatives within a degree of tolerable, from a business perspective, from a tolerable amount of certainty. So we don't want to turn off things that we think they might be bad, but we really don't know for sure, versus we also don't want to be overly cautious, like, oh, gee, there's 1 million impressions coming from this Time Warner person. So there's a balance we have to figure out, and I will be honest with you, it is tricky. But yes, we have to think about it quite a bit.
How do you measure your success since you never know for sure who's malicious and who's not?
One of the biggest things that is actually pretty exciting is seeing the change in how people respond to what we do. So as an example, I made these slides about 2 weeks ago, and I had a whole different set of IP addresses on here. And I was trying to finish up getting the data formatted, and I wanted to regenerate the tables and stuff so it looks nice. It turns out that some of the servers, the data centers we had identified some time ago, they had shifted their patterns entirely. So it was a different data center that I had on these slides, and I had to update it because we were successful at getting them to change their behavior. So I think one of the ways we can measure it is, do we cause new things to happen? So, because it's an arms race, right? So if it's a bit like Battleship in a sense, because you don't really know what's going on, but if you cause something to blow up, it means you did something. So that's one of the best ways we have to know the answer. There are, of course, a variety of vendors which will help you identify people who are known to have viruses and stuff, but there's no perfect answer to all of it, and it's sort of a fight until the heat death of the universe, or the end of humanity, whichever comes first.
So it's pretty clear there's a lot of actors out doing this. Do you have any idea how many you're specifically competing against?
No, we don't know. There's a lot of them.
So I could potentially just get a cluster on S3 and bombard you, get blacklisted. That way I won't get any impressions.
That's right.
Okay.
Yeah, AWS it's been blacklisted for some time now. So,
I mean, is that a problem though? Like, I don't want to see impressions. I mean, I go to a site.
Well, yeah, kind of. I mean, so that's getting into that question is more like, well, what do you think about AdBlock? And that's beyond my pay grade, so I'll pass that one off to someone else. I think AdBlock is, but I'll get a bit more serious. AdBlock is a serious problem, but I think it is a very different problem than invalid traffic. I would argue that invalid traffic is a lot worse because it undermines credibility of the industry, and I think it actually leads to sort of some of the issues. It's just my opinion, by the way. I'm not speaking officially or anything like that, but my guess would be that some of the problems that you have in the ad ecosystem are due to people need to make money, and it's because there's these problems with ad quality and traffic and stuff, and the more you can perpetuate bad actors doing bad things, the more those problems continue to exist. So if you can take money out of the system that are causing bad things to happen, it reduces the need for ad block. You can think about it a little bit like, let's say if the only people who bought ads on the internet were the Fortune 500 companies or something, you probably wouldn't have to worry so much about belly fat ads ruining your brand or virus ads or all these other bad things that happen. And the problem is that the market has issues with that sort of stuff still, and having illegitimate activity is not making the market more mature. So taking the bad stuff out on all ends of the system is important.